Mass is central to high school physics and applied mathematics, yet it is considered clunky in modern physics. So, what has happened to this once fundamental concept? And how do we know neutrinos have mass if we cannot measure it directly? High school physics still focuses on Newton's laws and the use of the concept of mass in mechanics. This is, of course, wholly understandable from a practical standpoint. Very few people will ever be in a situation where the fundamental awkwardness in the definition of the mass concept is important. But it can be a shock when a student learns that the concept has been largely abandoned in modern physics. Mass is a deeply intuitive, visceral, and real concept through the notion of inertia. First, it bears emphasizing that mass and matter are not key concepts in physics anymore. At the turn of the 20th century, at the time special relativity was being discovered, mass and matter were thought to be fundamental concepts. In the early years after the discovery of special relativity, some researchers tried to define a concept of relativistic mass that varies with an object's relative speed to the observation frame. This, however, is an awkward concept. Relativistic mass can provoke foaming at the mouth of some theoretical physicists, but it is not incorrect. It's just no longer very useful. To most physicists, when they learn this stuff, the first time they see mass, they think of the constant in Newton's second law. So, what's wrong with broadening this definition? Can't we define mass as the constant linking an acceleration with a force? You can, but it depends on the angle between the force and the velocity. The body's inertia is higher if you try to shove it along the direction of its motion than when you try to introduce a transverse acceleration. A moving body has more inertia along its motion than in the sideways direction. Now let's delve into the fascinating world of quantum mechanics to understand how mass and motion interplay at the smallest scales. One of the most groundbreaking discoveries in physics since the year 2010, one of the two most significant breakthroughs of this century, was the experimental confirmation of the origin of the rest mass of the W and Z bosons. These particles, which are indeed more massive than an iron nucleus, owe their mass to interactions with the Higgs field, a fundamental field that pervades the entire universe. Imagine the Higgs field as a kind of cosmic molasses. W and Z bosons would otherwise move at the speed of light, c, if they didn't feel the drag of this field. However, comparing this to pushing a ball through water can be slightly misleading. When you push a ball through water, the energy is lost to the water through viscous heat generation and ram pressure. Ram pressure represents the energy of motion that must be imparted to the water to make way for the ball. In contrast, when W and Z bosons interact with the Higgs field, the energy remains with them. If you try to stop a fast-moving W boson, the energy from the Higgs-W interaction is returned, adding to the impact force. This unique interaction was experimentally confirmed in 2012 with the discovery of the Higgs boson by the Large Hadron Collider, 50 years after the Higgs mechanism was first proposed. Unlike the interaction with an external field like the Higgs, this method involves particles confining one another. This is the nature of molecules and also of nucleons, protons and neutrons. These nucleons, in turn, are made of even smaller particles called quarks, which are held together by the strong nuclear force, mediated by gluons. Free gluons and quarks are theoretically massless, but they do not exist as free particles in nature. Instead, we observe and hypothesize their existence indirectly through deep inelastic scattering experiments, which are nuclear analogs of the atomic Rutherford experiment. This lack of direct experimental observability makes it challenging to confirm that gluons are truly massless. This is similar to how the momentum of light can give rise to mass. The force you feel as you sit in your seat is almost entirely due to the rattling of gluons binding the quarks in your body together into nucleons. These nucleons allow atoms, molecules, and ultimately your life and consciousness to come into being. But there's also a small contribution from the mysterious zig and zag. About 30 grams of that force is due to the rest mass of electrons in your body. Zig and zag refer to the mysterious self-coupling or confinement Dirac mechanism, which gives fermions like the electron and neutrino their rest mass, independent of external fields like the Higgs. One of the most groundbreaking discoveries in physics over the past 30 years is that the neutrino indeed possesses a non-zero mass. Yet, intriguingly, we still lack an accurate measurement of what this mass is. How do we know a neutrino has mass if we can't measure it directly? The answer lies in the phenomenon of flavor oscillation. Just as the helicity states zig and zag of an electron can interact and convert, neutrinos exhibit a coupling between their different flavor states. This coupling is enough to prove the existence of rest mass. In essence, rest mass arises from the interaction between otherwise massless states. The mutual conversion between flavor states of neutrinos is a telltale sign of non-zero rest mass. However, our measurements remain imprecise, leaving much to be discovered. In the quantum world, particles don't just exist, they dance. This dance is beautifully captured by the concept of Zitterbewegung, or jitter movement. To understand it better, let's revisit two captivating characters from our story Zig and Zag. These aren't just whimsical names. They represent the two coupled whale particles that make up an electron. When an electron is at rest, it doesn't stay still. Instead, it jitters back and forth between these two states at an astonishing frequency, approximately 100 million terahertz. This jittering isn't a random motion. It's a precise, high-frequency oscillation dictated by the coupling term m, which is a measure of the electron's rest mass. The larger the mass, the smaller the oscillation amplitude, and the quicker the transition between zig and zag. That was it for today. Until next time, stay curious and subscribe to the channel for daily videos.